So let's analyse our results then. We'll start with the resistor. So if you look at the data for the resistor, you will notice that the potential difference, we were increasing that by 1 each time, and the current was going up by roughly half an amp each time. And that was constant throughout, so it doesn't matter where we were in our data, it was always going up by the same amount each time. We starting at 0, 0, so it does go through the origin. We saw that we get something a little bit like this, straight line through the origin. You might be wondering why I've drawn the other 3 quadrants of this graph. Well, because I did actually mention this in the video. If you think about reversing the current, if you take the potential difference and you just swap the terminals over, you get negative values instead. Well, the exact same thing happens under reverse bias. So you get the exact same thing. It's just everything is backwards. Everything goes the opposite way. So when you put a negative potential difference on, you get a negative current. It just flows in the opposite direction, basically. If you push it the other way, it will flow the other way. So what do we call it when the data is in if you plot the graph, you get the data in a straight line, goes through the origin? Well, maybe you'll remember from my other videos, you get something called a directly proportional relationship. You double the voltage, you double the current. Yeah, and it's a straight line, it goes through the origin. This is something called Ohm's law. So these resistors are what's called ohmic conductors. So I'll just spell that, ohmic conductors. Ohmic conductors under constant temperature will follow a directly proportional relationship between voltage and current, or potential difference in current. So we can relate this to Ohm's law. We can say that V is directly proportional to I. Maybe you remember from maths that you could replace that directly proportional symbol with an equals and then some constant Ki, where in our results that constant K is just the resistance of the resistor. Yeah, so you might have seen this actually more written as V equals IR. Okay, voltage is current times resistance. Yeah, there we are. That's the resistor, or any ohmic conductor follows this relationship. It's a directly proportional relationship, straight line through the origin. Now, the filament lamp, slightly different. Remember what I was saying in the video? The filament lamp is not designed to continue. Is not designed as a resistor is. The resistance is going to change with temperature, in both cases actually, but more so with the filament lamp. You will have seen, if you looked at the results, you'll have seen that it starts off. It goes through the origin, and it starts off. The current starts off going upwards, but it starts at a point. It starts to go up by less and less. As we add more voltage, as the bulb gets brighter and hotter, the resistance goes up, so it becomes harder and harder to pass a current through it. So you see it sort of shallowing off there. Likewise, if we reverse the flow of potential difference, the bulb will behave in exactly the same way. It will light up, it will heat up, and it will be harder to pass a current through it. So you'll end up with the exact same thing at this end of the graph as well, in the negative bit, where it curves off a little bit. Okay, that was terrible. It curves off a little bit. Let me try drawing that again. Curves off a little bit at the end there. Okay, so it curves off. It becomes harder and harder to pass potential difference through it, so it flattens off. So a filament bulb is non-ohmic. It does not follow Ohm's law. Yeah, you could use Ohm's law at any point on the graph to calculate the resistance, but it's not. It's not ohmic. It's not ohmic. It doesn't follow a directly proportional relationship. It curves. Okay. The diode is a little bit more interesting. So what we saw was that it actually we didn't actually manage to pass. We had to turn up the voltage to a fair amount before we actually got any current out of it. So it was 0 until it got to a certain point when suddenly it started going up. And then you notice as well that as we went further and further up, the resistance of it was dropping quite significantly. So the current was going up and up and up until at some point when it just goes ridiculous, and it sort of just goes straight up like that. Yeah, we weren't able to go to these higher ends of voltages. If we put 10 10 volts across, if we manage to just put 10 volts across the diode, then something's going to break, really. Okay, the current will get too high, the power supply will cut out, or the diode will break, or something else will break. So you see it goes up like this. Now, something else that I'm going to mention about the diode, and I wish that I'd done this in the practical, actually. I wish I'd investigated this. But if you were to flip the diode around, in other words, if you were to change the potential difference from positive to negative, trying to push the current backwards, diodes don't allow that to happen. Diodes don't allow you to pass any current through under reverse bias, under negative voltages. So if you try to push it backwards, actually the current will stay at zero all the way along here. Yeah, so it doesn't, the current will not flow backwards. So there is our IV graph for a diode. So just to summarise, you got the resistor, straight line through the origin. You've got the filament lamp, curved line through the origins, flattening as you go higher up through voltage. And then the diode flattens completely under negative bias, but under positive bias, it will